Hello everyone. So today I want to talk to you about permittivity. So let me first remind you of our basic equation here relating D and E. D is the electric flux density in coulombs per meter squared. E is the permittivity, and we'll talk about that and what that actually means, in farads per meter. And E is the electric field intensity in newtons per coulomb, or equivalently volts per meter. So I want us to take some time to really understand the difference between what D is and what E is, and what this parameter permittivity, what that really means. To understand what D and permittivity is, I first want us to go back to the basics of what the field, so the electric field, is from a point charge here. So here's the formula that we've been using all along, and epsilon zero is the permittivity of free space. And essentially you can just think of this in the context of free space as like permittivity is like a constant of proportionality. And if you remember from Gauss's law, the integral of d dot ds, this is just equal to the integral of epsilon 0 e dot ds, and that is equal to the charge q. So in the context of free space, this constant epsilon 0, it really acts just like a constant of proportionality. Now I want you to consider what would happen if we took this point charge and we stuck it into some kind of non-conducting insulating material. We call it a dielectric. What would happen if we stuck it there? Would this formula still be true? Could we just use epsilon 0 and find the electric field? Would the electric field remain unchanged in the presence of some non-conducting material? That's the question I want us to think about. To answer this question, we need to think about what is the charge enclosed if we create a Gaussian surface. And before we answer that question of what is the charge enclosed, I want to first take some time to talk about the nature of dielectrics. All right, so suppose you have a dielectric material and you apply an electric field to this random dielectric material. Now, what would happen is, although you would not get an electric current flowing in this material because it's an insulator, you would have a redistribution of charges within the atoms and molecules of the material itself. So if I was to pick a point in this material and zoom in on it, in the presence of an applied field, my individual atoms or molecules would end up being polarized. One end would be positive and one end would be negative, and that has to do with the fact that you could say that the nucleus, the positively charged nucleus and the negatively charged electrons tend to be pushed apart when you apply an electric field. And so you end up getting this polarization. Now there are different kinds of dielectrics. There are some materials that have naturally polarized molecules. So whether you apply an electric field or not, it will still be polarized, and water is a good example of that. But the main point here is that while you can't get an electric current in a dielectric, you can get these atoms or molecules that have one side that's positively charged and one side that is negatively charged. And it turns out that understanding that is really important for understanding what permittivity is. So let's go back to our problem here. Here we've got a point charge, and we formed a Gaussian surface, and we asked, what is the charge enclosed if this point charge is embedded in some kind of dielectric material. Now, you might be tempted to at first be like, oh, well, the charge enclosed will still just be this charge Q because we assume the dielectric is neutral, there are equal amounts of protons and electrons, then it would just cancel each other out, and yeah, the math stays the same. But it turns out, because of the polarization of the atoms and molecules within the dielectric material, you actually will have a reduction in the net charge. So the result actually will be that the charge enclosed will be less than Q given the polarization of the material. And here's why. So notice if an electric field here is applied here from the point charge, these atoms and molecules will align themselves radially like this, in line with the electric field. And that makes sense, right? The negative charges are going to be attracted to the negative end is going to be attracted to the positive charge in the center here, and then the positive end here will go on the outside. And so you'll notice here that there are negative charges here that are contained inside the Gaussian surface, but then you have positive charges right here that are contained on the outside. So because these negative charges are just inside of the Gaussian surface, they subtract from the total charge Q. So the charge enclosed will actually be less than Q if you were to embed this in a non-conducting or in a dielectric material.
Hey.
Now, the amount of reduction in the charge Q, or the charge enclosed, will be dictated by how polarized the material is. So different materials will have a stronger electric field polarization in their atoms and molecules, and we use epsilon, or permittivity, to model how strongly a material polarizes in the presence of an applied field. So that is essentially what permittivity means when we're not working in free space, when we're dealing with a medium that has a bunch of atoms and molecules. So to account for this reduction in charge enclosed, we can redefine our permittivity from being epsilon 0 to a more general permittivity, and we can say that it's equal to epsilon r, or the relative permittivity, times epsilon 0. And this is otherwise known as the dielectric constant. So now, with that redefinition of epsilon, instead of epsilon 0, we do the integral of epsilon e, so epsilon in general, dot ds is equal to Q inside. Q inside is still this charge Q now. It's the Q inside is the net or source charges in your Gaussian surface. Because what we've done here is we've used this epsilon to take into account these other charges that you get from polarization. But the nice thing is now is that when we apply Gauss's law, we only have to think about what are the net or excess charges in the Gaussian surface. So in this case, Q inside here is just Q, and that's what you would plug in if you wanted to apply this. As long as you use the right epsilon for the material that's embedded in, it will automatically take into account this phenomenon involving the polarization of your atoms and molecules. So let's think about this from the perspective of the differential form of Gauss's law. So the divergence of D is equal to rho v, the divergence of E is equal to rho v over epsilon. So again, I want to emphasize that rho v in coulombs per meter cubed, that's your net charge density, or excess charge density. So if you have like a dielectric material here, and you sketch out a little tiny cube here in this, you would ask to find out what rho v is in that cube. You would ask how many more electrons or how many less electrons than protons are there. And so we're looking at net charge density. The cool thing about how we've defined epsilon here there is that epsilon then automatically takes into account the polarization of the material. So we don't have to think about that. We just have to think about the net or excess charges present. And notice here, according to this formula, that if you keep rho v constant, so you have a constant amount of charge, but you increase epsilon, E has to decrease. And that has to do intuitively with the fact that when the atoms or the molecules polarize in response to the applied field, they polarize in a direction, or they flip in a direction that counteracts the original field that caused them to align in the first place. All right, so let's talk about the difference between D and E, because I know for a while I was kind of confused about what the difference was exactly. So D is known as the electric flux density because integrating the flux over any surface gives the net charge enclosed regardless of the background material. Stated mathematically, we can say that the integral of d dot ds is equal to Q enclosed. Now let's talk about E. I've already said this before, but just to reiterate, E is known as the electric field intensity because it tells you the force acting on a charged particle if you placed it at a point inside a material or free space. So it doesn't matter whether it's free space or you're inside a material. If you place it at that point, it tells you the force on that charged particle. So simply put, the force is equal to QE. And this field E, that includes all the contributions, all the field contributions due to polarization and excess charges. So everything. It describes the net result of everything in its surroundings so that you know exactly what would happen to a point charge if you placed it there, and you would know that it would have that force. So I hope that gave you a better understanding of what epsilon and the difference between D and E is. Before I end this video, I do want to comment briefly on a few other parameters you're likely to encounter. So in addition to describing the relationship between D and E with epsilon, and then expressing epsilon as epsilon r times epsilon 0, you also can describe this relationship with a value known as the polarization, P. And essentially, you could think of this polarization as like a polarization field from the oriented atoms and molecules that adds in addition to the free space field that you get, this epsilon 0 E. And then we can also express the polarization in terms of this parameter here, epsilon 0 times the electric susceptibility, which is a dimensionless constant, times the electric field. And the relationship between electric susceptibility and relative permittivity is this. So I think it's just important that you know that these exist so that if you hear it, you can reference these equations. So thanks for watching, everybody, and I will see you in the next video.